Hello, this is the second part of the bipolar junction transistor. Biasing in BJT circuits. Biasing, like in PSpice we use the bias point. Biasing is how you connect, you do your circuit, you design it, and you can have the values of the currents IB, IC, IE, VC, VB, VE. So biasing, it's the way you connect your circuit to get your operating point. Here we are biasing it by the base. As you already noticed, we always have to put a VBB at the base and VCC at the collector. Here we are using only one voltage source, which is VCC. And you are taking from VCC to the base some energy. So your input will be VCC, RB, the transistor, and the ground. And your output loop will be VCC, RC, the transistor, and the ground. RBIB plus VBE minus VCC, because here you have VCC, equals 0. KVL at output, RCIC plus VCE minus VCC is equal to 0. This is a type of biasing. Another type is biasing by the emitter. You add a voltage source VEE in this direction at the emitter. And you will have at the input, here is the loop at the input and here is the loop at the output. At the input, you can have RBIB plus VBE. You cannot cross across the transistor and don't write anything. So you have RBIB plus VBE plus REIE minus VEE equals 0. And you know in an NPN transistor, VBE is 0.7. KVL at output, RCIC plus VCE plus REIE minus VEE minus VCC is equal to 0. Allow me to remind you that whenever you have the arrow, it's the positive of the voltage source. It is good to remind you that in all these slides for the bipolar junction transistor, we are using DC voltages. In this slide, we are biasing by collector feedback. So we are taking a part of the voltage at the collector and feeding it back to the transistor, to the base of the transistor. Here, I want you to be very careful about the currents. Here is the current IB, here is the current IE, and here is the current IC. IC is the current that is directly entering the transistor from its collector. You cannot write IC here, because here you have IC plus IB. Since here you have IB and IC, here is the sum. So here it is IE if you want. So for your transistor, the basics you know is IC, IB, IE. You have to place them directly entering the transistor. If we write a KVL at input, here is the input, it's a strange loop. You have RBIB plus VBE minus VCC plus RC times IB plus IC. I wrote it here in another way, minus VCC plus RC times the current IB plus IC plus RBIB plus VBE equals 0. Here you have VCC, so you have as if you have here a voltage source, VC, the positive is up and the negative is down. KVL at output, RC times the current IB plus IC plus VCE minus VCC equals 0. Please don't forget, you cannot go across the transistor and write nothing in the loop. Here is an exercise asking you to find all currents and all voltages, and given that beta equals 100. Here is the transistor. It's biasing by emitter. KVL at input here. You see, I put the currents IB, IC, IE directly entering and directly leaving the transistor. 47,000 IB plus VBE plus 4,700 IE minus 10 equals 0. KVL at output, minus 10 plus 1,000 IC plus VCE plus 4,700 IE minus 10 equals 0. And we know that IC equals beta IB and IE equals 1 plus beta IB. How did we get this one? It's IB plus IC, and I replaced IC by beta IB, and I put IB in factor 1 plus beta IB. And VBE equals 0.7 because it's an NPN type transistor. So from the first equation, you can get IB. And you know, in a transistor, once you have one current, you can deduce all the remaining ones. Here's IB from equation 1, and you deduce IC equals beta IB, IE equals beta plus 1 IB. VCE, you get it from 2, equation 2. I have to go back to the equation. And IE, how is IE? If you can imagine a little bit, you have at the emitter a resistance and VEE. So IE, it's VE at the transistor emitter minus 10 over 4,700. Do you remember it? You have to see it in the other slide. I don't know how can I do it here. And then you will get VE. VB minus VE equals 0.7. So VB equals 0.07 plus VE. VC, it's 9.76 plus VE. And you will get this one. As we said, anytime you find values, you have to check whether you are in active mode or not. NPN type, you have to have VC higher than VB plus 0.4. So in our case, VC is much bigger than VB plus 0.4. So we are in active mode. We are not in saturation. We are neither in saturation nor in blocking region. It's good. In this slide, we are biasing by voltage divider. It's a very important type of biasing. As you can see, you have as if you have a voltage divider here composed of R1 and R2. So the voltage at VB is taken from VCC according to this voltage divider. And since IB is very small, R1 and R2 can be considered as being in series. They are not, but they can be considered since the current IB is very small. So the current here is approximately the current here. And then you can write VB is approximately equal to R2 over R1 plus R2 times VCC. This is the voltage divider equation. We can, for more precision, use the Thevenin equivalent if you want. However, you can use this one. But for more precision, you can use Thevenin equivalent. V Thevenin equals VAB open circuit. So I have to remove the load. For me, in this exercise, I consider the transistor and its resistances as they are the load. So I will have only this circuit, and I will have to find VAB. This is V Thevenin. In this case, V Thevenin, since it is an open circuit, we are sure that R1 and R2 are in series. I can write a voltage divider perfectly. And to find R Thevenin, I have to look between A and B after deactivating the voltage source. The voltage source is deactivated by replacing it with a short circuit. So VCC here will be equal to ground, equivalent to ground. So whenever you look between A and B, you are here, you look here, you see R2 parallel to R1. Because R1 will be like this, and here you will have VCC equals ground. And R Thevenin is R1 parallel to R2. Here I put some note. We consider the transistor RC and RE as the load. We remove them to find V Thevenin since it has to be open circuit. For RTH, we deactivate all independent sources and we look between A and B. I remind you, we deactivate a voltage source by replacing it with a short circuit, and we deactivate a current source by replacing it with an open circuit. Great. Voltage sources are deactivated by replacing them with a short circuit. So VCC becomes 0. Très bien. Now that we found the Thevenin equivalent, we put back our load, the transistor RE and RC and VCC. It's perfect. You can write easily a loop here, a KVL at this loop, at the input loop, and a KVL at the output loop. It's a normal exercise. R Thevenin IB plus VBE plus REIE minus V Thevenin equals 0. KVL at output, RCIC plus VCE plus REIE minus VCC is equal to 0. Let me remind you of Thevenin, the use of Thevenin equivalent circuit. Thevenin replaces any complex circuit by a voltage source in series with a resistance. So any voltage source containing many resistances, many voltage sources, many current sources, when we do the Thevenin equivalent, it becomes equivalent to one voltage source in series with one resistance, such that V Thevenin equal VAB open circuit and R Thevenin seen with respect to A and B. Then we add back the load to a much simpler circuit, which is the Thevenin circuit. This is its principle. I wanted to talk about the Darlington circuit. It is used to give a bigger current gain. You place the emitter of the first one connected to the base of the second one, and both collectors are connected to VCC. We consider, to simplify the calculation, that IE is approximately equal to IC. So beta is approximately equal to IE over IB. The overall gain beta of this complete system is, as you remember, the current gain is I output over I input. So I output is I at the emitter 2, and the current at the input is IB1. This is the output, this is the input, and this is a system. We divide and multiply by IB2, and we know that IB2 is equal to IE1. The current here is the same as here. So you will get beta, the overall gain, equals beta 2 times beta 1, the gain of the second times the gain of the first. So, as you can see, this Darlington circuit amplifies the gain. Let us take an example. If beta 1 equals beta 2 equals 100, so beta equals 10 to the power 4. But in reality, the transistor will never give you this amplification. Will not give you an output current 10 to the power 4 bigger than the current at the input, because the transistor will saturate. Of course, however, it will amplify more than 100 times, but it will never amplify this 10,000 times, never. The collector won't be increasing, the current at the collector won't be increasing anymore. And we say that the transistor is saturated. Thank you. Here I added a slide that I wanted to share with you. For you, it's a good example. The transistors are used for many purposes. Amplification of current, on-off, remote control. One of these uses is to control another circuit of higher voltage and to work in a safe environment. For example, here you have the transistor with low currents, low voltages. It's very safe for you. At the collector, you place a relay. This is the inductance of the relay. And here in the relay, you have 3 contacts, 2 which are connected and 1 which is not. Here you place a circuit that is unsafe with higher currents and higher voltages. Once the transistor is conducting, there will be a current IC here that will excite this winding, this inductor. This contact will then come to here. And then you will close this circuit without putting your hands here. So as if you are controlling this circuit at distance. It's very interesting, don't you think? Thank you.